In this video, we are going to show how to do regression in R. So we are talking about linear regression. So we will start with simple linear regression, then extend it with more variables. And in the end, we're going to show some automated procedures for selection. Okay, so we are going to use as an example built-in data set. We're going to use the empty cars data set that's built into. We just made it into a table. Otherwise, it's built into R as a data frame. But since we are using in these videos, we are using the tidyverse, I do prefer tables. So I just made it into a table. This is data for 23 automobiles. It's a bit of an age, almost half a century ago, but still, what we have for these cars is we have the consumption and then some data about the cars. What we are going to do is we're trying to find out, what influences car fuel consumption. The consumption in the built-in data set is in miles. So what I did first is I did a transformation into something more European-like, because most of the audience for this video is Europeans. So basically I take the empty cars and then I mutate, I compute a new variable called consumption. So I'll take the empty cars. Then I just mutate, so I compute consumption from MPG. Basically I just transform the miles per gallon into liters per 100 kilometers of fuel using the formula. And then I just drop MPG by selecting everything that's not MPG. So this is what this command does. And yeah, if you wanna check what empty cars looks like now, so we have consumption in the end, and this is in liters per 100 kilometers, and all the other data there. Okay, so for simple regression, we might just do a linear model. So we'll make a model object called regression1, or just reg1. And for reg1, we define it so that we create a linear model. So we have an LM, it stands for linear model. We take data empty cars, the one we just transformed, and we try to put consumption as dependent on the engine power, so horsepowers. So the model is written just like this. So consumption is the dependent one, and then we have a wiggle, which means depends on, and on the right hand side we just have the horsepowers. So we can then take a summary of the model. So we get the model essentially. So the intercept is 6.44, so that would be the expected consumption with a car with 0 horsepower. Then with each additional horsepower, the consumption goes up by 0.04 liters for every additional horsepower of the car. The relationship is significant, and just with the power we are able to explain 58% of the variability of fuel consumption of these cars. We can also draw this. This part here draws the scatter plot. So if I just choose this part here and just draw it, so this is just a scatter plot. You can see it's quite a strong linear relationship, so we might claim that maybe it's not quite linear, that basically we start having some curvature here, but we won't make this extension in this video. Just follow up. There will be a follow-up video on regression modeling which will add this as well. Then I can actually add AB line. AB line will add the regression line. So AB line can be specified with a slope and intercept, and I just take the slope and intercept from the Reg1 model. So one part of the Reg1 object is coefficients. So Reg1 coefficients is basically just the coefficients of the regression. So this is just the coefficient, the intercept, and the slope for the horsepowers. So basically what this does, this calls the second element, which is the slope. So it will take this value, and this one calls the first element of the coefficient, so it will take this element. Well, then I just turn off the legend because I have more object. By default, ggplot will plot in legend, and I don't want it. So I'll just run this, and you see the fitted regression here. Now, if we want to test some of the regression assumptions, so the main assumptions we can test visually are normality of errors, homoscedasticity, and independence of errors, as well as have a look at the outliers, and the effect of some outliers. We may just choose to do an autoplot. So in order to do an autoplot of a linear model, we first need a library called ggfortify. So I'll just add this library, and then I can do an autoplot. Now, an autoplot for a linear model object will have 6 graphs. And I don't recommend that you actually plot all 6 of them because there's some overlap of information. Personally, I would recommend to choose first, second, fourth, and fifth. This is not the default option for plotting four graphs, but in my opinion, this is the best graphs. So if I run this, so first I have a normal QQ. Basically, this is testing is the distribution of errors normal, well, you might notice here that, well, we have a couple of elements that actually deviate from that. Also, I have some very high residuals here. So essentially, I have some units that stick out. So I have some potential outliers. So especially this 31, so observation 31, might be such that we maybe should consider dropping it from the regression and see if that has an impact on the regression, because it really looks like it's sticking out quite a lot. Okay. So this is some how to get the main diagnostics. Then we might start adding other variables. So for example, we might want to add the weight of the car. And so I just make a regression 2. And basically I just write a linear equation. So adding variables, it's very simple like that. So I just, add one more variable plus whatever on the right hand side of the wiggle. So basically I take more or less the same equation as I had before. I just, with a plus, add new elements like this. So computer rec 2, and yeah, what I get is, you see, added the weight of the car besides horsepowers. So the adjusted R square of the first model was 0.568. 8365, so it really pays out to add weight of the car besides the horsepowers. The interpretation, so as you can see here, the intercept is not even statistically significant, significantly different from 0, but that's not really important. Anyways, horsepowers, so with each horsepower, for the same weight of a car, the fuel consumption increases by 0.01, whereas for each ton of weight, the fuel consumption increases by 2.7 liters per 100 kilometers. And we might actually go and add more variables if we'd like. Just to remind what else could we, so for example, we could add the acceleration or displacement, for example, displacement of the engine. This is in cubic feet or cubic inches. I'm sorry, it's in cubic inches. So just to show you how you would do that. So let's just extend this. Add another variable. For example, I'd like to add displacement. Call this regression free. Regression free, like this. You might see the adjusted R-square actually dropped now, and also once I added displacement, you see the power of the engine, both power of the engine and displacement became non-significant, which might actually indicate that I have a presence of multicollinearity here. Now, and obviously, you know, I could do a diagnostics for this one as well, perhaps using the same graphs, not to revert to defaults. So I can do a diagnostics here for regression free. And as you can see, you know, the outliers are now different units. So I have now different units that stand out than before. So things might change when I add more variables. The last thing I want to show in this short video is how to use some automated methods of adding variables. Now, there are several libraries possible to do that. One that I find, so you can do it with the base R installation, so you have to add some libraries. One that I find quite useful is this OLSRR library that can do forward, backward, stepwise regression, and it can do that using different criteria. So it can use the significance of the power determination coefficient, or it can do it using the Akaika information criteria. So I'm not going to, in this video, I'm not going to go into details about which ones to choose. I'm just going to show you a little bit on how to use this model for forward selection or backward elimination using the significance of power determination. Anyways, first we need a full model. Oh yeah, by the way, if you want a full model, you can just take wiggle dot. Just make sure that when you do that, you have a data frame or table or whatever you have with just those variables that you want to use in the regression. So this would be the full model here. So basically all the variables are included. Now, you might notice here that even though the model is significant, none of the individual variables is significant, which might indicate that we have a problem with multicollinearity. But it doesn't matter. What we can do is, once we have this full model, we can use either OLS step forward or OLS step backward. The last indicates which criteria to use. So the P uses the significance of the part determination. Now forward, we'll just keep adding variables one by one while the coefficient of part determination is still significant. So what do we mean by significant? We determine with this p enter specification here, and well, we just make a new model there. Just call it forward fit, and we use OLS step forward p from the OLSRR package. We do this on the regression free, so the one that I just made here. And we use 5% significance of the part determination in order to enter a variable. Library first, okay. And can do a plot. Can see only two models were estimated. First the weight was added, and then horsepowers, and then it stopped. Because nothing else would be significant if adding anything more. This is the summary of this. We'll always print the final model, and the final model is actually the one that we've seen earlier when we manually entered horsepowers and then weight. Just the order of the variables is different. We might even go in the other way. So start with a full model and then eliminate the variables until only some of them are left. So that would be the backward procedure. So if I run this one, so plot here, might see in the plot there were 7 steps. So 6 variables were eliminated until we got the final one. So the final model here is a little bit different than the one with the forward. So everything is significant, but the variables here are, well, still weight, probably the most important one for determining fuel consumption. But we don't have the horsepowers, but instead we have displacement of the engine and the number of carburetors that it uses. So in brief, this is how we do linear regression in R. So thank you for your attention.